Hi, and welcome back to this class. And we're going to start lesson 3 this time, which continues on pointers. Last time we introduced what the pointers are, the concept of pointers, how to use them, manipulate them using the asterisk and characters, and how to manipulate memory based on pointers. Well, we're going to continue in this direction. And this time, we're going to talk about pointers and functions, basically how to pass parameters to functions using pointers. The second thing, we're going to talk about pointers and arrays, how to manipulate and access arrays using pointers. And then we're going to talk about address arithmetic, which basically how to manipulate addresses using pointers rather than using values or any other means. Okay, well, we're going to start from the first point, which is how to pass parameters to functions using pointers. In C, actually, arguments are passed by value. That's the standard C. And what do we mean by that? Well, simply, passing parameters by value means that when we make a call to a function, the function we're calling from is called the calling function, and the function which we go to is called the called function. Well, when I make a call to a function, I pass parameters to that function, because simply the called function is going to process these parameters somehow and return some results to the calling function. When we pass parameters by value, we mean by that I pass to the called function copies of the values of the parameters I'm passing. Okay, what does that mean? Well, that means there is no direct way for the called function to alter or change the original values of the original variables in the main program or in the calling function, because this function now works on these copies of the parameters rather than the original values contained in the main program or in the calling function. Well, this is a problem, I believe, and the problem is that you're gonna manipulate these parameters, change their values, do whatever you want to do with them in the called function, but now when you return from the called function to the calling program, all these changes are going to disappear, because basically what you're changing is copies of these, and you're changing locally the contents of these variables. But globally, when you go back to the calling function, values are still the same. So we didn't do basically anything as far as the calling function goes. Well, what we're going to do then? Well, simply in C, there's these magic pointers, which we already defined. Instead of passing these parameters by value, what we're going to do, we're going to pass pointers to these values and manipulate these values or these variables through these pointers and then go back. That way, yes, I'm going to another function in another scope, in another place, but however, my eyes are pointing to the original values actually in the calling function. And that's why when I make any change actually, I'm passing my hand, which is the pointer, back to the calling function and making these changes. And then when I return, I have physically changed the values of these parameters. And that's exactly what I want. Let's see how we're going to do this in C using pointers. We're going to illustrate this in an example. The example is very basic. Basically, we're going to build a swap function. And as you all know, swapping function is basically when you have two values and you want to exchange the contents of these two values or these two variables. Okay? And to illustrate the idea, I'm going to give a very simple example. The example is that you have an apple in your right hand and an orange in your left hand. And what you want to do is to swap these fruits in your hands. So you want, at the end of the day, to put the apple, which in your right hand, in the left hand, and put the orange in the right hand. Well, we cannot do it like that, because you're going to end up with no fruits in your hand, basically. Well, the basic thing to do, as we all know, is what I can do is to put the apple, which is in my right hand, on the table. So this is just a temporary place where I'm going to put the apple. My right hand is empty now. After that, I'm going to put the orange in my right hand. So this is full. This is empty now. And then I can grab the apple from this safe place, secondary temporary storage, to my left hand. So by that, I have now an orange in my right hand and an apple in the other hand. How to do that? That's what we're going to develop on the next slide. And on the next slide, I'm presenting actually two functions. One of them is called bad swap, and the other is called good swap. Why I'm calling them that way? Because this bad is actually bad. It doesn't do the task I'm asking for because of this passing parameters by value or by pointer. In this example right here, which we called bad swap, it's a function which returns a void value, which basically takes two parameters of type integer. The first parameter is x, second is y, and what I would like to do is to swap or exchange the content of x with the content of y. So basically, and that's the first thinking, beginners do that, I will define a temp variable, and that's basically the table which helped me making this swap in the apple-orange example I already gave. And then what I'm going to do, first thing, is to put whatever in x in this temp location. And then on the second line, I'm going to basically take whatever in y, place it in x, and then put in y whatever in temp and return, hoping that this thing is going to do the task for me. Looks fine, looks good. However, if we look deeper into it, I think we're going to all find that it's a bad example and it's not going to do basically the task which apparently looks like doing. Why is that? Well, simply because we have passed the value of x and the value of y to this function. So basically, yes, we have exchanged these values in here, but only in here. The original values in the main program, in the calling program, are not affected, not altered at all. And up to this point, down here, yes, the values are swapped. But once I do this, close the brace, and that means to return to the calling function, nothing has changed because the original values have not changed. Okay, let's see what's the alternative then, and what's the good choice of doing this. Well, the good choice is to do something like this. We call this function good swap, again of type void. It takes two parameters again. However, this time, these two parameters are pointers to x and y. Asterisk px and asterisk py of type integer. So they're pointers to integers, pointers to the values of x and y rather than the values of x and y themselves. Okay, and that's the I looking or pointing to the original values in the calling function. All right, and then I enter my function in here. The first thing I'm going to do again is to define some temporary storage inside. And there's no harm of using a value in here, a variable, rather than a pointer, because it's a local and I'm not going to use it. I'm not going to use it outside the scope of this function. So integer temp is sufficient. All right, and then, again, what I'm going to do, the first thing is to store in temp whatever value contained at this address. So what I'm saying in here is the value stored at px, bring it physically, place it in temp. All right, that's in a safe place now. Then after that, go physically to the memory at this address pointed by by, get it and place it in the memory location pointed by px. So I'm physically working on the memory here and not just on the variables themselves. All right, so by now, at this stage, the memory pointed by px contains the data which was contained at py. And then after that, I'm going to take this saved copy of whatever was contained in px and put it in the memory pointed by py. So what I'm doing in here, actually, I'm going physically to the memory, to the two locations pointed by px and py. Get the data in there. First, put it in a temp place, and then move the other content to the other address, and then back, take whatever you have saved in here temporarily, place it at the other address. And now you can return safely, and you can guarantee after this moment that actually the two values have changed as we want. To test this and to verify that what we're saying is correct, I have developed a simple main program which is basically going to test these two functions together. Because I'm going to be displaying some stuff on the screen, that's why I'm going to use the standard io.h library function, and that's why I made an include statement to it. This is very simple. And then after that, these are the two prototypes for the two functions, bad swap and good swap, which we have already talked about a few minutes ago. And then I'm entering here the main program. Okay, so main. Basically, I'm defining two variables in here. These are just test values. I'm defining two variables called a and b of type integer. And I'm initializing these two variables to be 1 for a and 999 for b. I'm going to use these, again, as test values. Okay, down here, this is a printf statement which basically displays whatever arguments it takes on the screen. Okay, so in here I'm going to display a equals and then the value of a, b equals the value of b, and this percentage d in here is actually the data format for decimals or for integers if you like. The /n, as you all know, is a no line. Okay, so basically this statement is going to display on the screen the value of a, value of b on one line. Okay, then after that, I'm making a call to this function which is called bad swap, which basically takes a and b as its arguments, the actual value of a and b. So I'm passing now by value. Copy of the values of a and b are going to go to this bad swap function, and then they're going to be processed. Once I return, I'm going to display the result on the screen for a and b as well. Same statement as here, but this one comes right after this, this function, after I call it. And then after that, I'm going to call the second function, which I called good swap. But this time, instead of passing a and b, I'm passing the address of a, address of p. So I'm passing pointers to this function rather than values themselves. All right? And then after that, I'm putting this display statement, printf, for a and b after the good swap function returns. Okay, let's see the result. I've wrote this program, compiled it, all right? And this is the result I got. Well, remember, the first printf I made was at the very beginning, right after the initialization. And this is just to make sure what values of a and b I have at the beginning. And again, it says here a equals to 1 and b equals to 999. That's at the very beginning. Looks good. That's exactly how I initialized a and b. Well, the second line actually comes in here. This is the first line, and then this is the second printf, which prints the second line, which comes right after bad swap function. Hopefully, I'm hoping to see the values of a and b exchanged. Unfortunately, what I see in here is that a is still 1, the same thing as before, b 999, the same as before, nothing has changed. So the swap didn't go through the way I like. And that's what I was claiming. And that's exactly proves the argument we're talking about. Yes, I attempted to swap the two values of a and b in the middle of the program, which is called bad swap, but physically, once I returned, these two values remain the same. And that's logic. However, I want to stress a point in here. If I make this printf as the very last line of the bad swap function right before I return, at that point, a will be 999 and b will be 1. Okay? So that's in the middle of the call the program. However, I'm going to return to the main program, to the calling function. And I want to use the new values of a and b when I return. And that's what I care about, not in the middle of the function itself. So that when I return, the values of A and B apparently remain the same. So the swap was not fruitful, and that's why I called it bad swap. Okay, but when I look at the third line, which comes right after the call statement, the printf statement in here, which comes right after this good swap calling statement, in which I pass the addresses of A and B, like pointers to A and B, see what I got? Well, it's exactly what I want. A is 999 and B is 1. So the task has been completed the way I like it. Well, and that's what we're saying. So then to pass, if you want your parameters to be changed, then you have to pass them by pointer. If you want your data or argument to stay the same, but you're going to use it to assign its value to other variables, then fine, you can pass it by value. Okay? So again, if you pass a parameter to another function just to use it, you're not going to change its value, it's all right to pass it as by value. However, if you want its value to be changed for whatever reason during your processing steps, then you have to pass a pointer to that value rather than passing the variable itself or the value itself. Okay? So this is the goal of this whole thing we're talking about so far. Let's see what exactly happens. This is very much repetition to what I've already said. In the main program, at the beginning, I have A equals to 1, B equals to 999. Okay, the compiler has already assigned 2 consecutive locations in the memory at these particular addresses. 4 bytes for A, 4 bytes for B. Initialization value of 1 in here, 999 in here. Okay, let's see what we're doing in this good swap function. Actually, the swap passes a pointer called px, which is a pointer actually to A, and pointer py, which points to B, to the swap function. Okay? So basically, I have defined these 2 variables down here, which they contain the address of A, address of B, right here. So that's what I pass. And this is the I actually on the memory when I go to the called function, which is the good swap. Okay, and then what do I say? I say, well, temp equals to whatever pointed by px. Okay, so temp is going to contain a value of 1, which is basically the contents of the location pointed by px, which is the content at this address. So I go to the memory at this address, take whatever in there, make a copy of it in temp. So temp contains 1. Good. And then what I'm saying in here is move whatever data you have at pointer py and place it in the location pointed by px. Okay. What do I have at py? Py is this. I go to the memory at this address. What do I have in there? 999. Take it and make a copy of it at whatever location pointed by px. Here's the location pointed by px. So go there and place whatever content down here into there. So I'm going physically to the memory to make that change. And that's exactly what I want. What do I have next? Well, I said, okay, now you go back and copy whatever you saved temporarily in temp, which is the 1, and store it in the memory at the location pointed by px. Okay, px contains this address. So I go to the memory at this address, okay, and I place the temp in there. Okay, so by that, I'm making the change. So physically, instead of having 1 in here, I'm having 999, and then I took the 1 and place it in here. So when I return now to my main program, once I'm done with the good swap function, A is now equals to 999 and B equals to 1, and that's exactly what I want. And this is the memory map which shows this. All right, so that's how we pass them parameters to functions using pointers. And we usually do that rather than passing them by value. Okay, in here it's just to remind you on the usage of the scanf. And remember, scanf is the function which we use to read data from the keyboard, from the standard input device. Well, if you all remember, we used the AND character before the variable we want to read. Like, we don't say scanf this is the format, and let's say capital. This is wrong in C because it assumes that it's going to get the value from this address, and it looks at capital as an address rather than a value or a variable. And this is not the way we do it. Instead, we say something like scanf %d and then the address of capital. So that means go to the standard input, get whatever value you're getting from the keyboard, and place it at this address, which is called capital. Okay? And that makes sense, I believe, because I'm going to copy data to the memory at a certain address. I'm not going to copy it into a value. That's nonsense. Okay? So that's the magical AND, if you like, which we use in the scanf function. Okay? Actually, this is the wrong statement I hinted to. If I attempt something like this, then scanf function will think that the value of capital is an address where the data has to be placed. And this is nonsense, of course, because capital is not an address in here. Okay, the second topic is pointers and arrays. Well, an array is basically a block of memory, contiguous block of memory, which contains data of certain type, predefined type. And I refer to any entry, to any element within that array, of course, using an index within that array. Okay, so to me, an array, let's say A of 10, something like this. If I define in C something like integer A of 10, this statement says reserve in the memory 10 consecutive locations. Each location is 4 bytes long, okay, and make the pointer A point to the first element, to the first integer in that array. Okay, so as a result of this, in the memory map, I'm going to be reserving actually 10 times 4 bytes. So 40 bytes are going to be reserved in the memory for this structure, and A is actually a pointer that points to the first 4 bytes or the first integer within this. Okay? So in C, there is a strong relation, as a matter of fact, between pointers and arrays. And as a matter of fact, we are talking about pointers in here. We're talking about A, which is a pointer to that array. And that's pretty much what we're talking about in here. So any operation that can be achieved by array subscripting can also be done with pointers. And actually, when I refer to any entry within this, within the array, I'm going to refer to the index of that entry. So A of 1 is the entry number 1. A of 0, as you all know, arrays in C start from 0. So the first entry has an index of 0. So A of 0, if I look at it, I'm going to show you a picture in a second on the slide. However, this is A of 10, and that means I have an array of 10 entries in here. Okay? And this is called A of 0. Excuse me, this is A of 10. Okay? So this is A of 0, and this is A of 1. So this is index 0, index 1, index 9, and that's how we define arrays in C. So we start, the first one is referred to with index 0, the last one with 10 minus 1, which is the 9. Okay? The pointer version will, in general, be faster, and we prefer to refer point to any entry within the array by using pointers, as we're going to see in a few minutes. So to define an array of size 10, we write something like integer a square bracket 10, and that means we're reserving, as I have shown you in here, I'm defining reserving 10 consecutive locations of type integer in the memory starting at this address. Okay, so it's something like this. This is my array, consecutive locations in the memory, referred to as A0, A1, A2, and so forth up to A9. What are the pointers so far? Well, we're going to see. A, as a matter of fact, which is the variable name we have used for the array structure we defined, is actually a pointer. And actually, A points to the first object in the array. And the object, in our case, in the example, is integer. So A actually is the address of the first entry in the array. Okay? And that's enough, actually, information about the array to access the rest of the parameters or the rest of entries in that array. So simply, I need the address of the first one. To go to the second one, I know that the second one is just one object ahead of the first one, and so forth. Okay, so in our case, since we're talking about integers, the first one is located at address A. The second element is located at A plus 4, which is actually the number of bytes reserved for each entry in the array. So generally, we use the notation A of square brackets I, and this refers to the ith element in the array. So in our case, I can be anything between 0 and 9 for this particular example. Okay, let's see how we can access entries in the array using the concept of pointers. Okay, for that, let's define PA, PB, PC to be 3 pointers of type integer, the same type as that of the array. Okay, and now we're making this assignment. PA, this pointer, contains the address of A0. Okay, so this is the same as saying PA equals to A. So PA is now a pointer, as we defined it in here, that points to the memory at this particular address. And that's actually the address of the first entry in the array, which is A0. Okay? And then, let's say PB is a second pointer, which points to the PA plus 1, and this means go to the next entry in the array. So this points actually to the second entry in the array. And adding 1 in here doesn't mean that I'm going to the second byte in here, but rather going to the second integer. So this is the first integer, 4 bytes, and this is the second integer. So when I say PB is this, and PA is this. Okay? When I say PC equals PA plus 9, 9 objects ahead. And that means go to the last element in the array. So PA is pointing to the first entry, PB pointing to the second entry, PC is pointing to the last entry. Okay? And it's obvious that the value of PA is not 2, of course. It's the address, actually, where I have in the memory a 2 in there. Okay. Address arithmetic. We can add, subtract integers to form pointers. And that's what we did actually on the previous slide. I have said PB equals to PA plus 1 plus 2 plus 9 and so forth. Actually, we're adding on these pointers. Let's see how we can manipulate more of this. when I add, subtract, or do any operation on pointers, actually the result is another pointer of the same type. It points to the same type of object after the addition. And we have to be a little bit careful in here, because when I say A is an integer array of size 10, then you make sure you don't go beyond this limit. You don't go beyond this address plus 9 to point to the last entry. If you go beyond that, that's not reserved for you, so you cannot write to that. You have to be careful about this. Let's see some examples and how we manipulate things. Okay, and here I have 2 pointers. One of them is called PA, which points to integer, 4 bytes in memory. Another pointer called is, which is a pointer to character, 1 byte in the memory. Okay, now if I say something like is minus 1, that means I'm pointing to the character just before this character. So this points to the character before is. 1 subtracted. Okay, here's is. Here's the memory. 2, 3, 4. This is pointed by PA of type integer. And then next, after that, I have a pointer called is. Okay, which is of type character. Pointer of type character. Excuse me. Okay, so if I say is minus 1, that means the object I'm pointing to, which comes right before this. So this is the address right before this address. So I'm referring to this byte when I do that. Okay, however, when I say something like PA plus 1, actually I'm adding 4 now to the pointer. I'm defining a new pointer, let's say PB, which is another pointer of type integer, something like this. Okay, so if I say something like PB equals to PA plus 1, this doesn't mean just 1 byte, but rather it means whatever size of object. The size of object this pointer is pointing to is 4 bytes long. So now PB is going to point to here. This is PB. I'm jumping 4 bytes in one shot. And we have to be careful about this. I'm pointing to integer. So go to the next integer. That's what it means. And when I say is plus 9, for example, I'm moving ahead 9 bytes ahead of this address. Okay? Because is of type character. So that's algebraically is correct 1 to 1 because it's 1 byte. However, this means add 4 because we're talking about blocks of memory of size 4 each. And when I say something like plus plus PA, this is a pre-increment of this pointer. So increment PA to point to the next integer, as a matter of fact. It's not just adding 1 to this address, but rather adding 4. Let's look at this example now. And in this example, we're talking about string comparison. Okay, let's say I have 2 strings. One is pointed by pointer 1 and the second by pointer 2. We're going to see them in a second. And I just want to return a value of greater than, equal, or less than. 2 strings are equal if they have the same exact set of characters. String A is greater than string B if the characters in here have a larger ASCII code, and string A is less than string B if it has lower ASCII. So pretty much to compare the 2 strings, what we're going to do is to start from the very beginning, point to the first character in here, first character in there, compare them. Okay? If they're equal, move to the next character. Equal, go to the next. Keep going till you encounter the end of character. If they're equal, return a value of 0. Otherwise, once you find a difference between the two, Okay, simply, if A is greater than B, then A minus B is some positive value. So that means greater. If A is less than B, then once you subtract them, you're going to get some sort of a negative value, and that means less. Let's see how we're going to do that, how to implement it. Okay, we're defining in here a variable called max len of 100, and that's the maximum size of the string we're defining. And we're having in here the prototype for the function which is called string compare. And basically it takes two pointers to two character strings, P1 and P2, and it's going to return a value of integer to indicate whether they're equal, greater, or less than. Integer getLine. This is basically a function which is going to allow me to get a line string from the keyboard. Okay? Let's get to the main function. Char A of max len, B of max len. I'm defining two array of type character, basically to hold the two strings I'm talking about, A and B. And then I'm defining a variable called comp of type integer, which is basically going to contain the return value from the string compare function. Okay, after that, I'm getting the first string, placing it in A, getting the second string, placing it in B. I have the two lines now. And now, I want to go to this string compare function, send A and B. In here, I'm sending A and B as values. And there's nothing wrong with this because I don't want to change the value of A nor the value of B. I just want to compare the two, if they're okay, if they're equal, greater, or less than. Okay? So what I'm going to do, basically, I'm going to call this function. A return value is going to come, and based on that, and I'm going to display a statement in here. If compare is greater than 0, that means the first line is greater than. If it's less than 0, that means the first line is less than the second one. If they're equal, I'm just saying they're equal. Okay? So the whole idea is in the string compare function. And that's how we're going to do it. Basically, these are the two strings. I'm going to make S point to the first character in the first, T points to the first character in the second, and I'm going to compare them. Equal, go to the second. Equal, go to next, and so forth, till I get to the end of the string, which is the null character. Okay? I reached a point where the two characters in here are not equal. So I stop right there, and then what I'm going to say is this minus this, they're going to give me a negative result, and that means S is less than T. That's pretty much what we're saying in this. Let's see the implementation. On this slide, I have two ways of implementing this function, the pointer version and the array version. I'll leave this for you to look at, and we're going to discuss this together. The pointer version. As I said, this returns a value of type integer depending on strings S and T, whether they're greater, equal, or less than. Okay, so in this, string compare returns this integer value, and I'm passing two pointers to the two strings, S and T. And I start right away with a for loop, which goes through all characters in these two strings. I start from the very beginning, and I keep moving as long as the character pointed by S equals to the character pointed by T. Okay, each time I'm incrementing these two pointers to go to the next character. Okay, and now I say if the character pointed by S equals to the null character, then apparently I have reached to the end of the strings, or one of the strings, and that's where I stop, I terminate. So I return a 0. That means I went through all characters, all the time, these two characters were equal. So if that is the case, return a 0 in here. And that's where I display in the print statement that two strings are equal. However, otherwise, that means I have returned because these two were not equal. In that case, what I'm returning is the character pointed by S at that moment minus the character pointed by T. And if this is greater, then this is going to be a positive value. Otherwise, it's going to be a negative value, which means greater or less than. So that pretty much summarizes what we want to talk about in pointers. If you would like to look at this array version of it, you can definitely go. always for other even supplementary material on the UNINETTUno website, and click on the MidNetU link, and you're going to see all the material you would like, exercises and examples. Thank you very much, and I'll see you later.